So over the last couple sections, specifically in 2.1 and 2.2, we've looked at defining what is position, what is velocity, and what is acceleration, how are they different, how are they related to each other. In addition, we've looked at different ways of interpreting the motion of an object, specifically through either motion diagrams or through position versus time and velocity versus time. This provides us with a measure of predicting qualitatively what's happening with the motion of an object. But if we want to predict what's happening quantitatively, aka with numbers and equations, we need to bump this up a little bit. So that's what we're looking at today, is how to quantitatively predict the outcome of a scenario with a given position, a given acceleration, and a given velocity, a field of study in physics that we call kinematics, the topic for 2.3. So some announcements real quick. We have Unit 2, Quiz 3 on Tuesday, October 20th. We have the Unit 2 notes and the Unit 2 test on Friday, October 23rd. If you are in, let's see here, 4th or 6th period. All right. And then if you are, let's see, do I have that right? 4th or 6th period? Yes. And then if you are in my 5th period class, you have this test on Thursday. So Thursday, October 22nd. Okay, so what we're up to today is learning how to mathematically model the motion of objects via the use of kinematic equations, how to apply kinematics to find solutions to physical scenarios, and yeah, that's about it. So kinematic equations, you do not need to memorize these equations. They will be available on quizzes and tests, okay? But still, choosing between these three equations can seem quite daunting, so that's what we're going to focus our topic on today, okay? So this first equation, we'll go over these equations here actually real quick, but let's go over what the variables mean real quick. So our key to the variables, x naught is what we call initial position, xf is final position, v naught is initial velocity, vf is final velocity, a represents acceleration, and t represents time. Okay? These equations were all found using calculus applied to the motion graphs that we looked at in the prior section, specifically position versus time, velocity versus time graphs. So this first equation right here tells us our final velocity is equal to our initial velocity plus acceleration times time. The way that we can make sense of this is that acceleration times time gives us a change in velocity. So we're having our initial velocity plus change in velocity gives us our final velocity. This second equation tells us our final position is equal to the initial position plus the initial velocity times time plus 1/2 times the acceleration times t squared. Please note that the time is squared, not the acceleration. So it's only the t being squared here, it's not the a. There's no real way to make sense of this equation right here unless you understand calculus, which again is beyond our scope for this class. And then this last equation actually comes from combining these first two equations. It tells you that your final velocity squared equals your initial velocity squared plus 2 times your acceleration times your final position minus your initial position. So these are our three kinematic equations that we'll be using for this particular section. So again, where do these equations come from? One word in one picture, calculus, and this guy right here, Isaac Newton. All right. Isaac Newton developed calculus, and he applied calculus to position, velocity versus time graphs we've been looking at over the past couple past couple lessons, and he was able to derive the kinematic equations from these specific combination of factors, calculus and position and velocity versus time graphs. So working with kinematic equations, let's jump into how to use these things. There's 3 of them, so it can seem quite daunting how to choose which one to use, okay? So let's take a look at example problem. A car speeds up from rest at a rate of 6 meters per second squared. How far will the car have traveled at the end of 12 seconds? Okay? How do we know which equation to use? How do we know what we're looking for? So we follow the steps below in order to resolve kinematic scenarios in order to organize these problem-solving procedures and make it easier for us to choose which equation we need to choose. So we write down our knowns and unknowns. Specifically, we write down what information we know and what the problem is asking us to solve for. Okay? So in this particular problem, okay, we can choose x naught to be 0 meters. We can always choose our initial spot to be 0 meters, okay? Since that's where we start measuring from. Our initial velocity here is 0 meters per second. We can't choose our initial velocity equals 0 meters per second. The initial velocity will either be given to us in a problem or not be given to us in a problem, okay? In this case, our initial velocity is 0 meters per second, even though it's not stated explicitly in the problem, because the problem tells us our car speeds up from rest, meaning our car starts off at 0 meters per second, okay? So a car speeds up at a rate of 6 meters per second squared. So this tells us our acceleration. Acceleration is equal to 6 meters per second squared. The way that we can tell is the units right here. Meters per second squared is our units for acceleration, okay? So that tells us our acceleration is 6 meters per second squared. Lastly, our time is going to be 12 seconds. T is equal to 12 seconds because it tells us how far the car traveled at the end of 12 seconds. Okay, so you need to make sure you know your units in order to be able to sift through and organize and identify what specific information is given to you in a problem. And then lastly, in terms of our unknown, we're looking for our final position x. It does not state explicitly that we're looking for our final position in the problem, but it asks us how far will the car have traveled. So that means we're looking for a final distance or a final position, so x is our unknown. Okay? So looking at our three kinematic equations, what we need to do now is use these variables to determine which kinematic equation is best to use. Okay? So we need an equation that contains x naught, v naught, a, t, and x, and that turns out to be our second kinematic equation. So we write down this second kinematic equation, okay? We don't start plugging in numbers yet. We write down this second kinematic equation, okay? So we get x equals x naught plus v naught times t plus 1/2 times a times t squared. The x naught we can set equal to 0 because that's what we have. And then the v naught times t we can set equal to 0 because v naught's equal to 0 and anything times 0 is 0. So the resulting equation we get is x equals 1/2 at squared. Okay? So as a result, we can now plug in our variables and our information. So a is 6 meters per second squared, t is equal to 12 seconds. So we're going to get 1/2 times 6 times 12 squared, which gives you a final position of 432 meters. Meaning Paul Walker and Vin Diesel have traveled 432 meters in their car at the end of the 12 seconds. So please be careful with your directions, okay? For these problems, you can always assume that your car is going to be heading to the right unless otherwise specifically stated. So as a result, if you're speeding up, acceleration will be positive, whereas if slowing down, your acceleration will be negative. So if this had said a car slows down at a rate of 6 meters per second squared, we would have a equals negative 6 meters per second squared, okay? And then lastly, our third step that we have right here is we solve for an unknown variable, which I forgot to highlight, but again, it's highlighted in all these three steps right here, okay? So now let's go through another problem together right here, okay? An aircraft carrier is designed to accommodate an F-22 Raptor, which has a liftoff speed of 76 meters per second. If the engine of the Raptor causes it to speed up at a rate of 11.35 meters per second squared, what should be the runway length of the carrier? Okay, so again, we go through our same steps as before. We identify our known information and our unknown information. So in this specific problem right here, all right, we know that airplanes are going to start from rest at one end of a runway. Even that's not stated explicitly, so we can set our initial velocity equals 0 meters per second. Okay. Again, this is not always the case, so please be careful to read for what your initial velocity is. Okay. When the F-22 Raptor, if we play a scenario in our head, reaches the end of the runway, it's going to be at its liftoff speed, meaning it's going to be ready to take flight. So our final velocity is going to be 76 meters per second. Okay. And then lastly, okay, we need to identify our acceleration. So we look for the word speed up. Okay. So we speed up at a rate of 11.35 meters per second squared. So this meters per second squared refers to acceleration. So our acceleration A is 11.35 meters per second squared. Okay? And then our initial position is 0 meters as usual. We can take the initial position of our plane at one end of the runway to be x naught, 0 meters. And then lastly, we're looking for how long should the runway be, aka how much distance is it going to take for our F-22 Raptor to reach 76 meters per second, reach liftoff. So we're looking for x, our final position. So now we look at our variables here. We have v naught, we have v, we have a, we have x naught, we have x, okay? In this case, it may be tempting to say, let's go back and use this kinematic equation right here, second one. But if we look, the second equation does not have time. Or excuse me, the second equation contains time right here, whereas we do not have time in this equation. Okay, we could solve for time, but that would involve us doing more work than we need to do here. What we can see is by comparing our variables, our knowns and unknowns with our list of equations, we can see we need to use the third kinematic equation. Final velocity squared equals initial velocity squared plus 2a times x minus x naught. Okay, so v naught squared is going to be 0 because our initial velocity is 0, and x naught is going to be 0. All right, so as a result, we're going to have v squared equals 2 times ax. All right, so we need to solve this equation for x now. So we replace v with 76, so we have 76 squared equals 2 times 11.35, okay? And solving this resulting equation for x is going to give you x equals 254.5 meters. And then lastly, we have an on your own problem right here. If you want to work out this problem by yourself, feel free to do so. You can pause the video at this time, complete your work, and then check with the solution. So we'll go through a solution right now. Per safety requirements, a train is required to brake to rest from a speed of 11 meters per second over a distance of 15 meters. What must be the acceleration caused by the brakes in order to achieve this? Okay, and this should say car, not train right there. It's a bit of a typo. So again, we proceed through our steps. One, we're going to write down our knowns and unknowns. So in this case right here, again, we can set our initial position equal to 0. We know our final position is equal to 15 meters because that's how far we're going to travel at the end when our car comes to rest, is 15 meters. Our initial velocity in this case is not 0 meters per second, but it's rather 11 meters per second because we're coming to rest from a speed of 11 meters per second, meaning our car is initially moving 11 meters per second, and then we're going to brake to a halt, to a stop. I combined two words there. So as a result, our initial velocity is 11 meters per second, and then our final velocity is going to be 0 meters per second because we're braking to rest, we're stopping. So our v equals 0 meters per second, that's our final velocity. And then lastly, it asks for our acceleration, so a is our unknown. All right, again, comparing our knowns and unknowns, we know x naught, x, v naught, and v, and we're looking for a. And with comparing that with a list of equations, we see that we're going to need our third kinematic equation again. V squared equals v naught squared plus 2a times x minus x naught. So as a result, we're going to get v squared we can cross out because our final velocity is 0. X naught we can cross out because it also equals 0. So we end up with 0 equals v naught squared plus 2ax, 2 times a times x. So we replace v naught with 11, so we're going to get 11 squared plus 2a times 15. We replace x with 15, and that gives us 0 equals 121 plus 30 times a. Okay? Solving the resulting equation is going to give us a equals negative 4.03 meters per second squared. One thing that I have not brought up so far is please make sure you have the correct units on your answer. Do not just state the number, but also state the units, because otherwise, if you just state a number, you are not telling me anything useful, you're just telling me a number. There needs to be a unit there because a unit assigns a physical significance to your number, okay? So we get negative 4.03 meters per second squared for our acceleration. We can check that this makes sense by looking at the fact that our car is slowing down in this case. Okay, we're braking to rest, so our acceleration should be negative here, which is what we get. So we can see that the mathematics and the theory matches up with conceptually what we would expect to happen. And this is the main idea behind kinematics.